Engineering rich internet applications with a model-driven approach. Okay, this paper starts off with introducing rich internet applications, and they compare to all the web applications. Rich internet applications support richer interaction mechanisms, animations, drag and drop, and so on. They also support division of work between the client and the server. In practice, we move away from thin clients toward fat clients, where we can provide a better user experience. And they continue with claiming that the introduction of new web technology requires new architecture, new best practices, and new methodologies. And they continue with mentioning advantages of using specific runtime environments, outside of the browser, Flash and so on. They say that the control logic can be implemented either at the client or the server. The business logic can be partitioned between the client and the server, and data can be stored at both the client and the server. Communication can be more flexible, because it can flow both ways, and the client can work while offline. And with the introduction of HTML5 and related standards, this will also apply to the in-browser environment. Yeah. The paper will investigate a model-driven approach for rich internet applications. And the research questions are: what are the architectural and functional features of rich internet application that make them different from traditional web applications? And which modeling concepts and notations do we need for these architectural and functional features? And can platform-independent models be used to generate code automatically? Yeah, they continue to find out, to look at previous research to find a common denominator, and the result is of 4 perspectives or sub models. First model is the domain model, used to represent business and data objects, properties, methods, and relationships. And we have the hypertext model, used to represent the composition of interface, pages and content navigation and so on. And we have the dynamic model, how the interfaces react to events. And we have the presentation model, look and feel of the interface. And they also continue with introducing a case, trip planner application, where users can book trips and so on. The case study is modeled using WebML and is gradually improved to incorporate RIA elements using ER diagrams and UML class diagrams. On top of the class diagram or ER diagram, a hypertext model can be defined. This is a site view with a recursive nested structure with pages, areas, content, and so on. The content is fetched from the data model by applying selectors, filters, and sorting parameters. Interaction is expressed at page level, area level, as a non-contextual navigation and at a component level, at a local level, called contextual navigation. Contextual navigation is navigation at the page level, and non-contextual navigation is navigation at the page level, where you can reach individual pages, and we have context navigation that is links and buttons and so on in widgets or yeah. WebML uses an implicit dynamic model based on the site view diagrams. This is modeled using a state chart. They continue with specifying requirements for RIA applications compared to the older web applications. We have data distribution. Data can be partitioned between the client and the server, and the client can operate offline. Thus, data location must be specified in the model. We have a computation distribution. Both client and server can execute business logic and extract data. And the same goes here. The model must specify where to allocate the computing. And we have a communication. Communication can be initiated by the server, not only by the client. Event processing can be both synchronous or asynchronous. And we also have page computation. Pages can be computed at both the server and the client. Yeah. Modeling distributed data. To model the data storage, both location as a server client and duration, persistence or temporary, must be modeled. This is done by tagging the model with an S for server and C for client by using icons. If it's not specified storage model, it's assumed that we use server and persistent storage. Modeling distributed computation. Computation can be done both on the server and the client, and how to partition must be specified. And you can do this in different ways, but possibly could be done just as a server or only as the client or as a combination. Yeah. The applications may need an execution engine in both the client and the server, and the client might be much more fine-grained. It must also contain the whole application. In the case of local data, there might not be the need for a refresh via the server. Okay. We also have some important features of the domain-specific language that it should be easy to use, intuitive, and not too detailed, and it should still be expressive. So to handle this, we need to specify computing at 2 levels: the client side and server side. In RIA, a page can be both computed and rendered by the client. This is split into server pages, calculated at the server and rendered at the client, and client pages processed and rendered at the client. Mixed combinations are allowed, and examples are server pages with client subpages and the other way around. To distinguish between server client pages, they are marked with C and S in the model. If nesting is applied and type is not specified, the outermost type is applied. And we also have distribution of component execution. Business components can be executed at the server, at the client, or both. This consists of multiple steps such as querying, filtering, and sorting. And the content may come from the client or the server. Some steps may be executed on the server and some on the client. An example of this is server-side filtering to reduce the data transfer to the client. Server and client units are marked with a C or S icon. If not specified, the type is inherited from the page. Modeling communication. In RIAs, events can be processed both synchron and asynchronously. And event filtering is used to specify how and where recipients are chosen. This can be done using the event publisher or an intermediate broker. Submitted messages stored until delivery. We have a model extension. Because RIAs allow collaboration and bidirectional messaging, events must be associated with a type to be filtered. Yeah. Okay. Okay, event notification and handling can be represented by using explicit operations for sending and receiving events. A send event operation is a notification of an event, including parameters and type, triggered by user navigation and so on. A receive event operation is an event listener as a subscription of an event type. Modeling page computation. In addition to the server-side controller, we have a client-side controller, and this results in 3 processes. One, the outermost page must be computed by the client controller. So some pages might be rendered from the server, or you have also partial recompilation of a page. And only the minimum number of affected components must be recomputed when receiving events. To model this, pairs of event computation sequences pairs are specified. So events can originate from users or the system, and examples of computations results can be content operation unit evaluation, content unit refresh, content unit invalidation, and content unit deactivation. Implementation. The modeling primitives introduced in the paper have been implemented in the web ratio, IDE, and support models in XML formats, data binding between model and data source, model validation, import of presentation mockups. The runtime is based on Apache, Struts, MVC2, and Hibernate. And the code generator transforms models in XML into components of the web project. And we have extended runtime architecture for RIAs. To support RIA, the existing architecture has been integrated with a client runtime environment with the following parts: controller for handling events, operations, and so on, model for client-side services, client-side state objects, and client-side storage, and a view for presentation components. So runtime and code generation extensions. Original MVC components were revised to support RIA additions. Sources for setting and retrieving parameters of events, sources for individual content and operation units, a generator to produce client-side code, a server-side generator to allow fine-grained invocation of content and operations. Experience and evaluation. The evaluation consists of 3 parts: expressive power. It must be able to address most frequent RIA requirements. Ease of use. The development methodology and notation should provide tangible benefits. And implementability. It should be possible to generate code from the models. Increase in expressive power comes at the price of a more verbose data and hypertext model. Examples of these are specification and persistence and location, specification of persistence and location, consistency problems because data requirements may be specified to both the client and server, and the specification of events. A way to handle this could be by using cloning wizards and multiple model layers and convert between the layers. Ease of use can be compared to manual coding and model development using traditional web engineering notation. Some advantages for model-driven development are independent abstractions, and code generation can help for cross-platform development. And we can reduce manual work for duplicating code across the server and the client. Implementability. They have identified some problems that need to be addressed, such as queries on the client relationships. Some older solutions use XML for data storage, which results in inefficient relation processing. And we have data transmission, server-side data used to populate client-side data requires data transfer. And we have presentation management. Page layout, user interface elements, not part of the WebML or the WebML extension. This is done deliberately to separate data and functions from the presentation. And if they say that presentation can be created by a graphic designer by using templates or something like that. And to include the page layout, you need to use blending functions and by using the code generator. Now we have the conclusion. They point out some of the prominent advantages of model-driven development, as shown in the paper. Those are the ability to explore different architectural patterns and the use of rapid prototyping cycles. Okay, that's it. Thank you.
Okay, thank you. Maybe I mean you looked at the papers, and this paper is very much, of course, then a model-driven approach. What do you say? Friendly. Can you say something about what you see as some of the challenges or some of the disadvantages of going in the model-driven way?
Yeah, so, as I mentioned in the end, I think it is easy that the model will explode with too much detail. That's maybe the main problem. So that we can solve this by using multiple layers of models and converting between them, but they haven't addressed this. And also the user's interface in the web applications is quite important, and they haven't addressed that as well. And I think that is we find the same things in many of the papers.
And there's also this whole issue about the model-driven approach would typically give you kind of a standard look and feel. It would limit your or typically the creativity, and for more advanced or yeah, for different types of applications, it may not be as suitable as it is for more standard, like in this case, traveling or shop type of application.
Yeah, the case example in the paper is quite simple, so it might not apply to real applications.
Exactly.
But this is the same things for all the papers. They just say that user interface should be kept outside using templates, so they don't want to address it at all.
Right.
So it's just maybe because it's too complex. I don't know.
Yeah, I mean, it's my feeling is that the model-driven approach is very good for where you also use templates for the websites as well. It's when it's just another web shop or just another organizational their web page to show their calendar and information of who's responsible for what. I mean, for just the standards, the type of applications and in this case they are richer than just the static web pages, but it's still probably not your first tool. Even though they say that you can allow yourself some rapid prototyping. Of course, the rapid prototypes will be kind of limited to the functionality that is easy to express in the models.
Yeah, and user interface is quite an important part of web applications.
I should say so.
So they should address it.
That's right. Okay, thank you. Let's see if we can move on to a different talk here. Let's see. This is the wrong room. Let's go there. It's waiting for something to happen. Okay. You have a presentation?
Yes.
There?
Yep.
You just hook up and I just turn around the camera. So this is opinion based. Do you want to sit where? Hopefully it is. So Marcus, maybe you just mute your microphone.
Yeah, sorry.
And you can turn it off if you have questions or comments.
I just saw that.
Yeah.
Okay. So my paper is the opinion-based collaborative filtering to solve popularity bias in recommended systems. As you can probably remember from last time, recommended systems are systems that are incorporated in for example, online shops that help users to explore more what there is on the product list. So they use these algorithms to recommend other items based on users' opinions. So this paper, so the summary of the paper says that so they introduced the existence and the effect of popularity bias in recommended systems. So there's this problem that the algorithm have been struggling for quite some years, and they also introduced two new weighting functions and an approach to solve the problem of the popularity bias. And they also to show that their method is effective, they conduct an experiment that demonstrates the effect of the new approach. So in the recommended systems, there is this problem called the Harry Potter problem. So most of the existing recommended systems suffer from this popularity bias problem. And popular items are always recommended to the user, regardless if they are related to the user or not. So, for example, the Harry Potter problem is the Harry Potter book is one of the most famous books out there. So every time a user is browsing other books, the Harry Potter book is always recommended from the system, no matter what type of books they're looking for. So so that is recommended items are biased towards popular and well-known items. And popularity bias recommender systems do not lead users to additional purchase because they might have made an like a decision about those popular items, so they don't need the system to recommend them again. Therefore, if you recommend a popular item, this might lead to the user for not purchasing anymore. So there's this lack of novelty. And because the popular items are always recommended by the system, those items that are less popular are less likely to be recommended by the system, even though they might be more related to the user than those that are popular. Previous studies on this problem exist, but as they mention in the paper, they have no systematic discussion about the problem. Another way of explaining the popularity bias is the Matthew effect. The Matthew effect says that so there is this phenomenon called where the rich gets richer and the poor gets poorer. So this is the Matthew effect, and you can see in these two figures. So figure 1A says that it represents the item rating frequencies and recommended items. As you can see, for example, the red lines represent the recommended times, and the blue line represents the popularity. You can see in the beginning that those items that are more popular are recommended. Their recommended times is way bigger, and as you go down, as the popularity decreases, so does the recommended times. And on the right hand side, we have the accumulative count of recommended times for items which are more popular than the target one. As you can see, the line goes up, which means that for those items that are popular, the recommended times is the same. Whereas for the items that are less popular, so the number of recommended times or the accumulative count is different. So at the end, at the head of the line, no matter how popular the item is, they get approximately the same recommended times. We go to the next one. So they propose two new methods to deal with the problem. And if we go back to figure 1B, we can say that recommended times for items are inversely proportional to their popularity. So the more popular the item is, the more recommended times there are. And recommended times for items are almost the same at the head, as you can see in figure B. And recommended times for items in the head and the long tail are different considerably. So based on these three points, they propose this base function, where PI is the popularity of an item. So the base function meets the three mentioned conditions for the recommended times for items. However, only the items at the head are affected by the Matthew effect, because they have the same recommended times, and they are the most popular items, so they get more and more popular. So that's why these items at the head of the tail, we need to reduce their popularity so that they will be recommended less. So therefore, if we treat all the items on the same way with that base function, this will not be appropriate. So what they do, instead of using the base function, they introduce the second function, which is the popular function, and so they divide the whole items into two subsets using a predefined threshold. So only the head set of the items are adjusted by the weighting function. As you can see, pH represents the minimal popularity of the head set. So if the items have a certain degree of popularity above the pH, then the popularity of the item is adjusted. So it will be less popular than it is. Whereas if it's less than the pH, then it's the function doesn't change, so it's just 1. So what they do, they use this movie lens data set where they have a lot of movies and a lot of ratings made from the users. So the ratings is in a 1 to 5 star scale. They use this 5-fold cross-validation for the evaluation of the items, and they use also 80% of the original set for training and 20% of the evaluation for evaluating the result. And so to compare their new methods with the existing ones, They evaluate the accuracy using this NDCG, which is the normalized discounted cumulative gain. And for diversity, they use the coverage and coverage in long tail. As you can remember, how the recommended system work, they have this similarity function of the users. So what they do, they select, using the similarity function, they select a certain number of neighbors which are similar to the user, and then using their ratings, they can predict the user's rating for a movie that the user has not seen yet. So what they did, they used the size of the nearest neighbors was 50, which was just an empirical value that they used, and the threshold to divide the popular items between the less popular items was selected to be 0.5, as this was the best one while analyzing the impact of the threshold. And we can see later on the table, which illustrate the results of proposed approaches and the comparative ones on a top-end recommended tasks on this movie lens dataset. For each column in this table, they highlighted the top 3 best performed methods. So user collaborative filtering is the first one, which was the traditional one. Has the best performance in terms of accuracy. You can see it's bolded, while the item collaborative function and the item collaborative function is PP are the old ones, and they can see that they are best. They get the best diversity and the worst accuracy. So the first 3 lines are the accuracy, and the coverage and long tail are the diversity values. So these were the upper ones were the old methods, which they used to compare with, and the last 2, which is opinion weighting user collaborative filtering based, and so the last one is using the popular function, and the previous last one is using the base function, and we can see that they both do well in the accuracy and in the diversity, but the opinion weighting user collaborative filtering performs best on both accuracy and diversity. You can see the last one; it's highlighted. All line is highlighted. That's why this function has performed best, and this is also the function that was proposed by the authors. This verifies, so because the opinion weighting user collaborative filtering function performs best on diversity and accuracy, this verifies that the effect of very popular items should be adjusted. If we go to these 2 figures, we can see that the impact of the threshold value, which was used from 0 to 1 using a 0.1 step, it can be seen that the 0.1 value showed to be the best in performance. So that's why they used this threshold for the experiment in their data set. As a conclusion, so the experiment results show that the proposed approach to the opinion weighting user collaborative filtering approach outperformed the baseline and the baseline and the comparative ones, which were user collaborative function and item collaborative function in terms of accuracy and diversity. The experiment verifies also the effectiveness of the proposed approach. It also verifies that there is a problem called popularity bias in the recommended systems. And what they want to do, so as future works, they want to explore further functions as weighting functions And they want to try also different data sets because there are available data sets there, except the movie lens. For example, the Netflix data set that we talked about last time. So yeah, it's a bit confusing with the algorithms, but so the main idea was to reduce the popularity of items. So when you
well, I guess you can reduce the popularity, but you can use the impact of
the popularity. Yeah. So they wanna do that, and as they said in the paper, previous studies have been done, but not in a systematic way to explain the problem at hand, step by step. So
maybe if you go back to the experiment slide. Do you all know what the fivefold is and the difference between the training set and evaluation set? These are known terms, or maybe you can explain what this is all about, because it's typical for these kind of experiments, these kind of studies. That's to get some good results. Maybe you can explain it.
Yeah. So what they do is they have this movie lens data set with the ratings, and they use, because before they try to make recommendations, they have to make a user model, and to make a user model, they have to use this. They have to use a set to train the algorithm in order to make recommendations. So what they do, and the whole data set, they take 80% of the original set for the training of the algorithm, and then to validate or to evaluate if the ratings are are accurate, they use the 20% of the set to make the evaluation. And the fivefold cross validation, I'm not sure.
Okay, so let's think about it. 20%. So you have 100%. So divide it into 5. These are all 20%.
Should I flip the camera?
You may want to.
Thank you.
So what you do is that for the next experiment, you do this, and then these are your training sets. And that's the evaluation set, that's the evaluation set, that's the evaluation set. So on one data set, you get 4 experiments, and you average the results. Because if you just pick one, you can have a little bit of randomness there. But now you split them into 5, and you use 1 as your evaluation set, and the 5 others or 4 others as training set. And in the fivefold, you do this 5 times. And then you average up the number, so you are less relying on how the data was actually split. So that's a quite common approach. So that's what the fivefold is. Make sense?
And that's why it's 80 and 20.
Yes, because then you divide.
And 20
so if you reduce this number, you could get a 7-fold or a 10-fold. So it depends a little bit on how big your data set is. But 80-20 is quite common at 5-fold. But you can create larger or average over more. If you have large sets, you can pick a different number than a 5-fold. 5-fold is quite common. Makes sense? Good. I think we just go on and go through the 2 last presentations and then have a longer break in the end. Is that okay?
Yeah.
We can carry on. So, Nikita, you want to?
Yeah, but probably we need to connect because there is no HDMI here, right?
We still don't have that HDMI converter now.
We can connect to your, I sent you a presentation. So it's okay. This is not so good to show all this, but all my emails. But let's just I don't remember.
Which paper is it?
Sorry?
Which paper is it?
No, it's just a presentation.
Okay.
So it's not one of the papers. But where did I do with it? When did you send it? It was
It's not that one
because it's not.
we can maybe search.
Yeah, no,
Yeah.
this is not the final one, is it? Or link? Oh yeah, the link is. This is the one.
Recommend.
Just choose it here. Marcus, you can see it?
Yes, I can.
Okay.
And still?
Yeah. Today we are going to talk about demand-driven architecture. And the first I want to start with motivation, why it was developed, why we need to have something new. And then I will try to explain what's like the main principle of it, and several implementations that were developed recent years in this field. So motivation. We have now web applications that are spread, and compared to older years, they are much rich. They have their own local state. They also have the remote state, which we have to handle. These web applications, they're usually components-based nowadays. Either it's React or Angular, it's still like small components which we build our application with. The problem is that our UIs are trees. I mean that we build our application starting from the root, and we have nodes in the end. And each component is like another part of the tree. But the problem is the data is actually a graph and not a tree. And it took quite a while for people to understand that. I will explain what does it mean later. The next problem is that we have really big variety of clients. We have mobile clients, we have desktops, we have laptops, we have like small devices like watches now. So we have, and we have to support all of them. We have to support, we have to make possible for these clients to work fast, not that we will increase like data transmission or something like that. Most of these devices have big problems with latency and bandwidth. So we have to think about these problems. And recently, Internet of Things appeared. So like it's additional set of the clients, possible clients to our APIs and like applications that we build on top of them. So currently we have so-called supply-driven architecture, and the like most famous example of this approach is the REST. So what does it mean is that our backend, why it's called supply-driven architecture, because our server provides with data, meaning like that's what I have, and you can make requests. I will return you this data, but everything else is up to you, what you are going to do with it. So that's what I have, and just your problems, how you will reshape this data, what you will do with it. So what REST does is it defines logical resources that usually map to our database tables. But the problem is that what clients should do if they want to have joining resources, meaning that like the joins of database. So we have user, and we want to have also know their friends. So we have to join this table. We have to join this resource, and we have to first ask for a user and then ask for his or her friends. So we have to make 2 requests because there is no other way, or we have to put all their friends inside one resource, which is also bad because then we'll have a much bigger resource. So this is a common problem in REST with joint resources. Multiple requests. So we have endpoints, and to render our application, we have to make a request to each of them to get data, and then again repeat requests for joint resources. So it's a lot of multiple requests, which are really bad for mobile clients with their high latency, bad bandwidth. We have diversity of clients again, and the problem is that we can't predict the future, meaning that how usually REST build is that we have some endpoints, and then we need to add some other fields that we want to support. We add to this resource a couple of more fields, then a couple of more fields, but we never can think about the future, what kind of clients will be supported, what they will need. Like now we have to have mobile clients and laptop clients, desktop clients. So usually for mobile clients, we have to have less data than for desktop clients. What should we need? Should we do? We should have different API for them that will support less data and then repeat our code, or we have to use the same API and then get data that we don't need. So and we can't know for sure what kind of clients we will use and what will appear. So we have to be more flexible in that way. So instead of supply-driven architecture, demand-driven architecture is proposed. And the core idea of it is that we have users, or clients, they specify so-called demand, or it's also called query, as a data, which is declarative and composable, meaning that we can have small queries, so small demand for each component, and we can compose it in a big query or big demand for all our application. Just build it from down to top of our UI tree. So we have some demand, meaning that what we need to render this particular component, this is some data that we need. And service have to fulfill this demand by sending this data. It should be data source independent, because nowadays we use a lot of big variety of databases. We have to support any kind of them. We want to have easily switch between them. We want to we want to be data source independent in our applications. And what we also want, we want to have same solution for local and remote state of application, because sometimes we have some state on our clients, but then we decide to put this on backend, on server side, and we don't want to change our client's code. We want to be flexible on that as well. Unfortunately, not all of the implementations support that. That's why the star is there. But at least that's the goal, and probably it will be in the future even in those implementations. So the interesting thing about this kind of technique is that it was developed simultaneously by 2 independent companies, Netflix and Facebook. They were developed approximately at the same time. I looked at when was made first commit to their repositories, and for GraphQL it was August 2015. For Netflix Falcor it was February 2015. So it's like a year ago. They both started to work on the same thing. Interesting thing that Facebook has a monolithic approach as their like architectural overhead application, and Netflix is microservices, and they still came to the same solution. So it doesn't, it's not doesn't matter what kind of architecture you have. You still have the same problems, and you want to solve them in some way. So what Facebook did is that they developed their own graph query language. That's language that queries graphs. And Relay is the library that combines GraphQL with React, which was also developed in Facebook, meaning that you can have your React application, your React components, you can annotate them with GraphQL demand queries, and you will get your data. I will show examples later. And Netflix made their Falcor. Falcor is also JavaScript library, client-side JavaScript library for applications. And they use JSON graph as their approach of graph data. I will show as well examples later. We also have, then after these big companies developed their own approaches, it was also developed ClojureScript library called OmNext. It was next generation of Om library. This interesting thing here is that instead of inventing something new, they just took the best from both approaches and adopted it, and that kind of showed itself to work really good. So we'll start with Falcor, Netflix library. So we have this web page where we have docs, documentation, we have reasoning behind the Falcor, but the basic the basic information is on this page. So the core concept is that we have our service site, which has different databases, different data sources, and we have one entry point which is called API, which defines so-called model JSON file in which we have all the description of everything our service can provide. It's like full API that's combined in one JSON file, and clients using this model request data from this service. So Falcor is the part of the Falcor is on client side to make particular requests to service using the model, and the part of the Falcor is on the service side to know where to take what data, because we have different databases, different data sources. So that's how request to our service looks like. We say that we want these particular fields, and return the service returns us a JSON file. So we have, like, we requested user name, user surname, and user address, and we have completely like the same, like what we asked. That's what we get, what we got. Not nothing additional, not other fields. We just asked for user fields, and we got them. So to understand where we can, like, from which data source we can take our data, Falcor provides with so-called router, which kind of similar to routers in web frameworks, which specify, which matches the URLs, but instead of matching URLs, here we're matching JavaScript paths. So what we have here is we create new router. We have pass set, and here we have comment that pass set can be like user name, surname, user surname, name, and like all combinations of fields. So we have
Question.
Yeah.
Path set is what you specify in the URL, the get parameter.
Yeah, you don't specify it by hands, but you use library, yeah, and then it just sends this path set as a query parameter. So and then we have user service that matches this user, like this path, and we get our current user here, for example, is just like as example. And when we get our user, we then return only those keys that were specified in our path. So we don't return anything in addition except what was specified in our request. So what this router allows us to do is, for example, we have some recommendation database. We have recommendation service. The router stands between our client-side application and this database, these services. So we have, for example, general list with name drama, for example, and we have titles of movies from this genre, and we reference, as you see, titles by ID 2, 3, 4. So meaning that in like movie with ID 2, 3, 4 is part of the drama genre. So to get the title of this movie, we can use another service, title service, that's reference the movies by IDs, and we can have name, we can have year, description, and so on. But we then router decides where we get this information if we need it. So if you will ask generally drama, get me movies names and years, it will understand that we have to ask recommendation database, we have to ask title database to fulfill our client-side demand. And the same with rating. So it allows us to have separation, and since Netflix is microservices based, it's like suits them perfectly. So data is an API. Again, we specify our request using data. What they proud of, or what they can emphasize, is that the way you get data from your services, from your Falcor model, is the same way you get data from just JSON objects in memory. So if you would just, like they have this example, so we have our user that's just object on client side, and we want to get user surname, we just model.user.surname, do these things. So when you move to Falcor, what you do is just you create new model, Falcor model, you have some cache, and you have user inside, so pretty much the same. The difference in getting the user surname is that we specify it as a string parameter that pass to our data, and it returns futures. So we have to wait for our results to be fetched and then print our surname. So our communication becomes asynchronous. That's the only change. To change this data is stored on client side, so we don't have any communication with the service for now. But when we want to change and have our user database, it's useful for prototyping. You can just put your data inside client side. Don't wait for backend guys to implement API. You just have it on client side, do your queries, render your pages, and then, for example, they finish to implement backend. You can now specify, instead of going directly from cache, you can specify source, where like your model JSON located, and you can query now remote service to get your data. So they have this diagram. We have client side, we have use that communicates through cache inside the model with data source. Like all communication with data source and view is happening through cache. And we can specify the cache size. We can specify, like, because for different devices, different cache size is suitable as well. So it's quite flexible in that sense. Data source communicates using this model JSON with our API, and where we have our router that asks for particular data from different services. And yeah, they say that it suits our MVC model view controller architecture. The only difference is communication between model and view becomes asynchronous instead synchronous. So I'm not sure I have it. Yeah. So that was Falcor. Again, core ideas of Falcor is that we have single JSON resource for all data that describes our all data. Clients request only what they actually need, not full data. They get not full data, but just what they need to render particular component or particular page. We have the same approach for local and remote data, or local and remote state. We have single request, which is to get all data you need to render your application. And that's important because when user opens your web application on mobile device, what you want to do is get as fast as possible some initial data from the server and render the page without having this long spin of loading the data from different resources. So you want to make single request with like to eliminate latency as much as possible and render the page. And it has caching, quite flexible caching that we can specify the size for different devices. The next thing is Relay that was developed in Facebook. So I can start with showing GraphQL language, just to show how it looks like. So
It's running slowly. Just let it work. It's powerful.
So GraphQL language is the language that completely separate library developed in Facebook that helps developers to specify the queries to their data and get results in the same shape you specify your demand. So here we have that's how query looks like. So we want to have to query hero entity, and we want to know their name. So this is the result. So it has the same shape instead of this data, but we can just eliminate it. So we have hero, the name, R2D2. We can also have nested, like, because it's GraphQL, we can query graphs. So we can have hero name and their friend's name. So friends can be the same entity, like some user in database, and we just go recursively making a like recursive query inside. So we have name R2D2 and his or its friends' names. So we get this result which has the same shape as our request. That's really convenient in applications. We can also have parameters to our queries if we want human with particular ID. And again, we get the same, what we asked, that's what we got. So no extra data again. So completely the same approach, even though it was developed in completely independently in different company. So yeah, we have like different, we can specify different parameters. We can have aliases. We can, we can have fragments, which defines like part of our queries, which is used then in Relay library. But that's at least how our queries looks like. And that's how Relay looks like. So Relay, as I said, is kind of middleware between React components and GraphQL. So here they have example. We create component profile picture. So the meaning of this component is to just show profile picture with some UI. We have function render, which is called on when state is changed, and it expects to have user because we're showing profile picture of particular user, and we expect in this user to have profile photo URI. And here we want to also have some sliders that can change the size of this photo. So now we defined like demand for this particular component or query that's need to be sent to service to render this component. So we specify query. This is all comments. So we just specify that fragment on user. So here we say that we want some part for fragment from user entity, a specifically profile photo with parameter size and its URI. And they call, like, because React has components and they call containers, which is on top of these components that can communicate with GraphQL. So they create this container based on this component we defined previously. We have some initial variables like size. And here is our GraphQL query. So users, profile photo, its URI. So that's how the structure looks like. So we have React components, which are supplied by some data given from containers, Relay containers. And this Relay containers communicates using GraphQL with some store and get some response, and then just call React component inside. We can easily add some additional data that we want to, because like we have profile pictures and we want to change something. We want to show also, I don't know, like, so here they show size now. They just specify that they want variable size, and that's how they change it. So whenever size is changed in this function, Relay makes request to service to get new picture URI for this particular size. And only when this request will come and we will get some results, only then this component will be rendered with a new size applied, with a new URI applied. We can easily compose this containers the same way we compose React components. So we have, for example, now profile component, which has profile picture component and specify user for this component. We also want to show name of the user in this profile component. And now we're going to define query for this root component. It has to have user's name to display it here, and it has to have everything that profile picture wants to have. So that's the way how we compose our queries. And the full query, GraphQL query will look like that. So we have our profile on user, which wants name of the user and all information that profile photo wants. Profile photo wants profile photo with particular size and its URI. So that's how relay looks like. So here we have UI is a tree of composable declarative components, which is actually just React library. All components are annotated declaratively with what they want from service to render this particular component. So they specify their demand particularly in component. Yeah, we have data masking, meaning that just to prevent encapsulation, it's called when we don't want child components to see the state of the root component, and we don't want root component to be able to access child components, this field, because it can be changed, and then our root component will not work. So they have this data masking to prevent that, and they use GraphQL API to communicate with their services. The next technology is OmNext, this library, and here we have really good blog post that tells their good experience of using Om in their application, and why they wait when OmNext will be, because it's now currently in alpha, so they're waiting for a new version. So here we have more kind of broad explanation of why we have this revolution of UI in general. So they have their own web application, CircleCI, which is just bigger web application with a lot of graphics, with a lot of possibilities to do. So they start to explain why we actually need React, because Om library is the wrapper of React, JavaScript library, React, but with their own additions. So they explain it in the way that, let's say we have some groceries list, and we want to insert new broccoli in this list somewhere here. So there are two approaches to do this. Either we find the particular place to insert it in. That's the way jQuery works. But then it's kind of error-prone, and it's really hard to find this particular place. And if it will change its place, then everything will stop to work. So it's kind of low level. Or we can say that we will re-render the full list from scratch. We'll remove this list and we'll create a new one. But then it will lead to a lot of re-rendering of the page. It's like crazy amount on each change just to render all the list. So what React does is that it provides us with tools that we think that we create new list and we re-render the full list, but we actually manipulate not the actual DOM on the page, but we manipulate virtual DOM. So they, in really smart way, they see what actual changes to the web page, to the page they have to make to fulfill all differences that we made. And they do this quite often. It's like they have even frames per second, so it's like a game engines stuff. So they now say why they want to have OM, because OM provides with application state as a single immutable data structure, which allows us to make a transition between one state to another in atomical way. We never get the state of our inconsistent state of our application. It also enables us to do really just in 5 lines of code to make undo operation in our applications, to just to store previous state of our application, to save it somewhere in the list, and then just change it back. So it's, and having just one state, we allowed to do this. And because they were using cursors, that was because having one big state like this, grocery list with different names, and when we want to render only this particular item, we have to know where it's located in our state, and that's bad, because then it's like, then children know the structure of the state. It can change. It's not good. So what they did is they actually provide these small components with cursors, which points to a particular place in our tree, which is our state. And then we can kind of query. They just provide with the path to this node, and we can query to it, and we can change it in the same way. We just change it by this reference, kind of reference, and without knowing where it's located, actually. But the problem was with, for example, deletions. The item, when we display items and we have to have the cross that deletes this item, then item have to delete this field from the state. But the problem is that it's not the item, you have to delete it from the list that's root of this item, but you don't know where it is. So now you have to pass this list to all items components, and that's very bad. The way OM solves it was through queues, which is good, but it's like additional abstraction to have. So now OM next fixes everything. So what we have now, we have the same one state of our application, but now the state is the graph. That's another problem, is that state is not is graph and not tree. So in new version of OM next, they solved it again the same way Falcor did that. Now they have this mutation the same as GraphQL has, that we specify what we want to change, and then we have separate logic that that triggers these changes actually, so that item components doesn't have to know where it's located. And also they have the same way Falcor did. We have local and remote state handled in the same way and transparently for web application. So we can look through this. So it's the same components-based architecture, the same as React have. It's declarative data dependencies, the same as Relay have, but their own syntax. They have so-called reconciler, which is actually Falcos router, the same thing. It just knows where to ask different data from. It have query syntax that was taken from the Atomic database, so they were not inventing something new. Database by itself is also very interesting, but yeah, it suits also this architecture good. And data graph similar to JSON graph that is in Falcor the same way. So the last thing I wanted to talk about is why we talk about graphs, why we're not satisfied with trees, what's wrong with trees, having data as a trees. And I think good article about this was written in Falcor in their JSON graph post. So the thing is that even though our UI set trees, we usually have graphs in our applications. As an example, movies in Netflix. We have recently watched components, some list of movies that references movies, but we also have new releases that also references movies. And it can be that they reference the same entity. So here we don't have tree here, we have graph here, because two nodes reference one thing. So before Falk or before JSON graph, the way to solve it was to have a copy of the same data in two nodes. But the problems then is that when you change, they have this example with rating, you change rating in your recently watched movies, and then it's inconsistent with the state in new releases, because you change this copy but not this, and you have to manually go and remember where all the copies of this data is to change it. So it was really error prone. And the way to solve is to have some kind of structure that can reference entities by their IDs. It's not something new, but it was something new for client-side development, and it's represented as a JSON object. So what they have here, for example, they have to-do list. So we have to-dos, and we have two items there, and we reference these items by ID, and we have kind of store of this to-dos in our separate field. So that's kind of the way to solve this problem, by having JSON format as a tree-based format, and we want to represent graph in this format. So that's the way they solved it, and it's completely the same way Omnext solved their problem. They also have these references. They also Falcor or Omnext provide you the transparent way to go from these to-dos. You want to have name of your to-do. It's transparently, you can't see these references. You just ask for a name or if it's done, and it automatically finds where it's located in this graph. Yeah, so that's kind of why we need graphs and why trees were not suitable. And yeah, why I put question mark here is that it's interesting. They call GraphQL like graph query language, but the thing is that what they return as a result is actually a tree and not a graph. They don't have any references. They return copies of, like, if you will ask for a friend and you will ask this friend in some other place, it will be two copies of this friend. So they query graph, but they return a tree. And true graphs that's returned are in JSON graph and Omnext. That's kind of interesting thing about that. So what are results of this new architecture? We don't have data reshaping, because before that, with REST architecture, we had to reshape our data that was just resources into some trees that then have to be rendered on our trees UI. Now we don't have, everything is made automatically. We have one initial request to render our application. Users are not annoyed now. No extra data transmission. We get only what we ask and what we need to do to render our application. We decouple client and service implementations, meaning that clients, they can ask their demand independently of what servers provide them. I mean, of course, servers have to provide what they ask to do, but they can also provide with a lot of other things that's not influenced. Clients will not know about this new stuff, never. So they can they claim that they solved this version of API problem, because you don't have to have versions. You just can add things to your graph API, and it will just, and then new clients will just ask for new data. You don't need to create new version of it. It's easy to extend again, just adding new data to your graph API. And this interesting thing that none of this actually, at least as far as I was reading and as far as I know, none of this implementation reference, interesting thing is that this approach can be used to communicate between services, not only between client or web applications and service, but between services by itself. There is development in that area as well. There is a library that allows you to specify graph API, so-called, that you can communicate between the services, but it's still early in production. And yeah, for some reason, maybe GraphQL will be used for that for services. I don't know, but at least none of this implementation talks about that. So challenges. Yeah, the thing is that in all of these implementations, they tend to say that everything is good. They pretty much never say that's what's our drawbacks of this. And as we know, nothing can be given for free, except if we previously were using resources not in a good way. Not all resources will be used. So it seems that they tend to say that that's the case. We were not using all resources, and we just optimized our solutions. But what I at least see that challenges here are that you have to support some completely new domain-specific language that you have to implement on your server side to understand that it's not that easy, this language, because it's recursive. You can have infinity number of nested entities to ask. The problem is that when you have this nested possibility to have nested recursive queries, is that you have to prevent users at some point to do this in some way, because then it's easy to just DDoS your server with just simple requests with 100 recursive depth, and your database will just die of this query. So you have to be kind of, by giving more possibilities to a client to specify what data they want, you have to restrict them in some way as well. You have to have some security levels. So we have extra work on server side, because all these libraries are developed by front-end guys or girls, like people, and they don't care much about backend. Like I as backend developer can see that, because they say like, oh, everything is awesome on client side. Yes, but what I should do on server side? Because the problem is that you have different sources, you have different databases, and you have to parse this query language to get resources in some crazy way clients want them to have, in any way they actually will want ever to have. That's not easy task to achieve. And yeah, hard to write efficient backend query resolver. Current implementations of backend, they tend to be more like toy examples. They are not very efficient in the way that they can produce n+1 queries very easily. When you request, or for example, you can request one entity like 100 times, just the same entity, just because it was appeared in different parts of the graphs, and they do not kind of solve this issue. Recently, Facebook published their way to solve this, at least proposed way, and it uses caching and batching, which is a bit hacky way. It's like solving consequences instead of the problem itself, I feel like, by having caching of queries. So it's really hard to implement this, and like most of the implementations just follow these simple solutions where you can introduce these n+1 queries pretty easily in your applications. So there is work to do. The only thing is, on Next propose to use Datomic as a database backend, And they say like you can just use it because of the specific approach Datomic use, because it's not relational database, but it's like more logical database that use data log language. It's like predicates. It's a bit similar to a Prolog if somebody used this language to query the data. So there you can solve this, but not all of your data can be stored in Datomic, and I don't think that everybody would switch to it. So it should be some way to do that addressed. So yeah, that's pretty much all.
Can I ask a question?
Yeah.
Does any of those frameworks say anything specific about authorization? For example, if I should see certain attributes in a certain object that, for example, Lars shouldn't see, and vice versa.
Yeah, so that's actually another challenge I had to add it here, because none of them specify that. They tend to put this responsibility on some other layers that you have to implement. I haven't searched for actual implementations. I think there should be some. But again, yeah, that's kind of your problem to specify what users can access what API parts. Shouldn't be impossible, but should be some implementations, I think. But yeah, still it have to be addressed. It's not addressed in their, this GraphQL is just graph query language. React is just relay is just between them, but there is nothing about authorization there. You have to find something by yourself. And the same with other languages and approaches.
Okay. I don't think we have time for you're gonna have that faith every time. Next time you'll be first.
Yeah.
Give you a time slot. I think till next week, maybe I've been in touch with quite a few of you, and been leading you on the way to find or narrow down and find the direction you want to go in. And some of you have already come up with some proposals for papers you would like to include. So I think for next week or for the next weeks, because we won't fit all of you in the next seminar, I would like you to start picking out papers that you think fit. And if you need some assistance, then send me an email and see where you are at. And I'll have a couple of meetings already with some of you, and going through some ideas and sketch out a little bit what the way could be like. And so I know that global software development is taking a bit of time, it's supposed to do, but if you can by end of Thursday have one paper that you think you would like to introduce and discuss with the rest of the group. And of course, you will find many more papers for your report and for your project, more than the ones you present. But if you find a paper and send it to me as well, and I'll, or if you have they have several alternatives, just send it to me, and I'll go through and see which ones I think will be the better ones, so fit better. And by Thursday, so if you can have it by Thursday, then I can set up a list of who's going to go next week and the week after. This is going to be for 2 weeks because Nikita's presentation was a bit longer, but other than that, we'll typically be able to do 4 presentations in one seminar. And we do 4 next week and 4 the week after. So you already have your papers out next week, so
yeah.
That's fine. You're like, yeah. But for the rest of you, if you can send me by end of Thursday. Yeah. Any questions or comments or? And as I said before, if you need help, if you still find it difficult to narrow down or difficult to find papers, just drop by my office or send an email or just get in touch with me. Very good. Thank you. So Marcus, you also send me your suggested paper?
Yeah, we'll do that.
Perfect. Then
Okay.
we'll meet again next week.
Yeah, we do. Bye.
Bye-bye.